All righty. Without further ado, Ralph, you want to take it away?
Sure, and I'm assuming everybody can see my screen.
Yes, it looks good.
Excellent. All right. I can figure out how to put together plans to design an interstellar probe, but working a lot of buttons on many of these platforms is something I'm still coming up to speed on. Well, again, good morning, good afternoon, good evening, good day, whatever. I know we've got a lot of people that are spread out around the globe. And so what I wanted to do was to give you a bit of an overview, digging a little bit back into the history as well of all this. I mean, again, this is nothing new. Michael was off on one thing. Actually, the NIAC work that sort of got us started at APL wasn't from 2009. It was from 1999. So we've been thinking about this for a while. So as Michael was saying, this is a pragmatic interstellar probe, and just to elaborate on what he was saying, that it's really about a mission through the outer heliosphere into the nearby very local interstellar medium. And an important point is to use today's technology to make this step. There have been a lot of efforts that have been talked about in the past, and because they have had to draw on things that did not exist, they tended to get kicked down the road. And the issue is to try to be able to pave the way for more ambitious future journeys, but to be able to look at something that would be compelling now and to see if it is compelling now. And again, this is one of the things that we would like to hear from the community that we've assembled both here, and tell all of your friends as well that we would like to hear from them also. So right now with the study, Michael alluded to this, we had phase one actually started in June of 2018 and went for a year. It kind of got us started, had it enable us to have sort of some handshakes with the people at NASA headquarters and get things well defined for doing an engineering study. There was actually an engineering study that was done on solar probe that was funded by the Heliophysics Division for about a 4-year period starting back in 2002. And that really was key to leading up to the launch of Parker Solar Probe, of course, in 2018. So right now, this next phase concept development that started in July of 2019, it nominally runs through the end of April of 2022. We'll have a technical report to be delivered in late 2021 for input to the next Solar and Space Physics Decadal Survey. The plan is also to be attending a lot of meetings and being able to brief the community. And hopefully by late 2021, we'll be able to talk in person. We'll see. So to really go back to the beginning, in the beginning there's a confluence of ideas. TRL 0, technological readiness level 0. And it's sort of interesting, if you look at the history of astronautics, it really all goes back to Jules Verne. And it really goes back to From the Earth to the Moon that he penned in 1865. H.G. Wells, of course, followed with his War of the Worlds. Wells himself said that he was inspired for his spacecraft for the Martians to be coming into landing on the Earth by the gun canister that Verne had come up with for getting his astronauts to the moon and back. Well, there's also knowledge that you have to throw in, that sort of TRL1. And I highlight the Curies because, of course, following on Becquerel's discovery of radiation in 1896, the Curies jointly were awarded the Nobel Prize for Physics in the early part of the 1900s for the discovery of the radioactive elements polonium and radium. And you say, well, what does that have to do with any of this? Well, it turns out that this was really the beginning of that long road toward figuring out how to do power supplies that you could actually use in deep space. And I'll say some more about that. The other piece is that all of this inspires those who follow, TRL2. So, of course, I think many of you have know about the Tsiolkovsky equation. Of course, Konstantin Edvardovich Tsiolkovsky worked pretty much by himself, but was really sort of the father of rocketry. He recognized that the best kind of rocket fuel was liquid hydrogen and liquid oxygen. Again, around the turn of the century, and had worried a great deal about how that one could travel to the moon and to the planets, and really started putting in some of the engineering expertise. Astronautics in France had one of the first airplane licenses in France and was the key to the development of astronautics in the continent. Of course, Robert Goddard in the United States, and then of course Oberth as well. We'll be talking a little bit more about the maneuver that follows his name. So the idea of the travel, the space between the stars and the stars themselves is certainly not new. So I mentioned about Tsiolkovsky. He published his investigation of outer spaces by rocket devices in 1911, talked about the idea of using radioactivity perhaps as a means of coming up with a better power of propulsion. Robert Goddard pinned the ultimate migration on the 14th of January, 1918, and talked about the necessity of beginning to think about what it might take to travel outside of the solar system someday. And again, looking back at this new phenomenon of radioactivity and whether that was some way of unlocking that power source to be part of that study. Mission need and demonstrated prototypes. Well, we had World War II with the V2, which was really the development of the rocket, and of course nuclear power. All of these led to a lot of money being put in that would probably not have happened otherwise. It's an unfortunate fact of our times, perhaps. But it turns out that one of the needs that was identified in the United States at the end of World War II was the idea for having reconnaissance satellites. In 1946, it was a highly classified program at the time, all since declassified. And they identified the need for having a 500-watt electric power supply on board a satellite. And that's where, with the current radioisotope power supplies that we're flying today on the Voyagers and New Horizons, actually came from. So it was alluded to that there were 3 special probes in March of 1960. This was from the new Space Science Board panel that was called the Simpson Committee, because John Simpson, who of course had a variety of, he was at the University of Chicago and flew a variety of instruments in space, was the chair of this. And at the time, people were wondering about, okay, so we've got this capability of going into space and doing things scientifically. What should we be really thinking about doing? And they identified 3 probes, one to be a solar probe to go near the sun. Of course, we launched Parker. One was a probe to go perpendicular to the plane of the ecliptic. And of course, we've flown Ulysses. And another one was an outer solar system probe to be aimed away out of the plane of the ecliptic. Now, it's interesting to note that in writing in 1960, they said that they hoped that a speed of, to the extent of 5 or 6 astronomical units per year would be feasible by 1965. And of course, the fastest thing that's traveling out there is Voyager 1 at about 3.6 AU per year. So the propulsion has always been a challenge. The rationale has not changed, though. George Sutton, writing back in 1961, noted that with respect to spaceflight operations, that the first principal objective is the scientific exploration of space. And of course, Sutton is known to some of you in the engineering side especially as literally being the person that wrote the book on liquid rocket engines. And his obituary was just published by the AIAA. He passed away in October, 1 month after his 100th birthday. If it hadn't been for Sutton, rocketry and astronautics would not be where that they are now, and there would be been no Saturn V, and there would be no Space Launch System or Space Shuttle. So for any mission, if you think about it, I think there are 4 elements that you can have to look at. One is that you have to have a case for going, and that's the science, and it's also round up into politics, because these things are not cheap to do. But you also have to have the means to go, and that means you have to have the technology out there, and it has to be ready if you're going to actually build something. You have to have an agreement to go, and that's a strategy. And our strategy documents that we have these days are the decadal surveys that are done by the National Academies, and of course we're working on those right now. The planetary one is in place and running, and the solar and space physics one will be following soon thereafter. And then finally, you have to worry about the funds, and this was alluded to earlier. You have to have policy that's encoded into law where that there are funds available for actually doing these things. My claim is that a well thought out systems approach that incorporates all of these key elements is really what you have to have a successful exploration plan, and that goes for any of its component pieces, such as an interstellar probe. Now, certainly the science questions are not new. There was a large JPL study that was done in 1976, 1977. Of course, the eve of Voyager, the Voyagers launched in late August and September of 1977. The article, Science Aspects of a Mission Beyond the Planets, published by Jaffe and Ivy and Icarus in 1979, outlined most of the science questions that we're still talking about today. The big problem was, how were you going to do that? They came up with a concept using a nuclear electric propulsion system that had a 32,000 kilogram launch mass and needed a very large nuclear electric propulsion system, which they said that they did not know how to build, and we still do not have one. So you'll be hearing more about these later. Pontus Brandt will be talking about the interstellar probe science goals and opportunities. It really is about our habitable astrosphere. And again, this traces back to the same questions that have been asked all along about this. The primary goal being our habitable astrosphere and the unexplored interstellar medium. Right now, we know of one astrosphere that is habitable, and we live in it. There's also the question of things that one could do with this as a platform for doing astrophysics and for doing planetary science in the platform, and you'll be hearing about that, and again, a lot of discussion about that during this workshop. You'll also be hearing about a notional science traceability matrix. Many of you have been working on this, contributing to it, and Pontus Brandt will be leading some more on this as well, and we're trying to get that distilled down into something concrete, which is something that you need for a mission like this. Now, what we've done is to adopt a menu approach. And the idea is to engage the science and technical communities. This is a good example of that. And really to put together a menu of what we can do. Then it's a question of ordering from the menu is something that at NASA's discretion, it will be up to a science definition team. NASA so chooses to set one up. But at the same time, you'd like the assurance about which orders can be placed and what they would cost. And you have to worry about inflation as well. I ran across this. This is a menu from Delmonico's in New York from 1899, and the expensive thing on the menu were the Carnadoza fillet of beef for $2.50. There's been a bit of inflation since then, so one has to keep that in mind. Again, the central technical question has always been propulsion, and one of the issues has been that these near future capabilities that people have advertised have always been the backdrop for defining requirements. But the real issue is to unite compelling science with engineering and technical reality. And again, that's what we're really concentrating on this particular excursion. So the engineering requirements, readiness, launch no later than 1 January 2030. By being able to set that means that says something about where we are with the technology. Operate from as far away as 1,000 astronomical units. Looking at 600 watts of power at launch, at half of that after a 50-year time, down to 300. And then actually, again, designed for the lifetime of not less than 50 years. And these were set up in order to at least start up the various engineering studies. We've been working with colleagues at Marshall Space Flight Center now for about 3 years, looking at what one can do with this Space Launch System, the SLS, the Block 2 cargo version, and with various upper stages, basically looking at putting a third and a fourth stage on top of an SLS and using that to get us to extremely high speeds. We're looking at probably around twice the launch energy of New Horizons, which is the fastest thing that we've ever gotten off the planet. Right now, we've got 7 different things that are going on. You'll be hearing about these in depth from everybody. We've got a study on longevity. We're, of course, looking at instruments. We're looking at the trajectory and the launch vehicle, communications and guidance and control trades. We're looking at a heat shield and heat shield materials to see if one could really go close to the sun and do an O-berth maneuver, a powered solar flyby, which because you can't go at night. You have to really worry about the thermal constraints, and those, it turns out, are very, very daunting. And then finally, we're working on a mechanical design, and we're also dealing with some of the power issues as we go as well. So you'll hear more about the reliability and longevity. Again, this is the idea of what you would need to do to design a 50-year mission. We've been looking at a lot of instrument possibilities, and again, we're still collecting data on these. We're interested in hearing from the community. The question is, looking at what we need to measure, what can you build, and what sort of masses are those things going to come in at in order to be able to actually make the measurements? And one has to be realistic about this. Again, I'm not going to be able to build a 2-meter class telescope for 2 grams. That's not in the cards. The physics simply is not there. An exaggeration, but one runs into this in these discussions nonetheless. So the mission concepts are all ballistic. We haven't looked at low thrust in space concepts because we're limited by their low mass to power ratios of what we can develop right now. We're looking, so you'll hear a lot about these options, option 1, 2, and 3. Option 1 is an unpowered Jupiter gravity system. 2 is taking one of the stages with us to Jupiter and actually firing it close to Jupiter in Jupiter's gravity well. And 3 is doing this powered solar flyby. We've looked at 22 different staging cases with the SLS, and the guidance and control and the thermal studies are all ongoing. You'll hear a bit about that. We've got a large telecommunications trade space. This is just to note that what we're looking at right now is probably X-band with a 5-meter diameter high gain antenna. And there are a lot of reasons for that. There's going to be a detailed discussion of these capabilities and why we ended up there. Again, we're looking at the thermal limits of shield material. We've been working with Advanced Ceramic Fibers, ACF in Idaho Falls, who one of the experts right now in how far up in temperature you can take materials before they fall apart, and seeing what one might be able to do with some of that technology. This gives you an idea of the mechanical layout we're looking at right now for an all-heliospheric science payload with an option 1 trajectory. This is a spinner. Jim Kennison will talk some more about that. The power requirements are very close to historical. Right now, NASA and DOE are working on the next generation RTG. It's a derivative from the GPHS and MHW RTGs. And what we need is really fairly close in terms of efficiency and lifetime for use. And of course, the MHW RTGs are on board Voyager, been operating successfully for 43 years now, over 43 years. And it's a GPHS RTG that powered, well, several of them have powered Galileo, 1 powered Ulysses, 3 powered Cassini, and 1 is now powering New Horizons. So one scenario that we've looked at to have a launch as early as the 24th of February 2030. This is this piece of this animation is from our colleagues again at Marshall Space Flight Center. This is what the SLS Block 2 would look like on liftoff. A bit taller than a Saturn V, similar class. Of course, SLS is being built right now for the Artemis program for human capability of getting to Mars with a translinear injection capability of around 45 to 50 metric tons. I've got solids that have been derived from the space shuttle program, and those get us up to an initial orbit so that we can go faster and onward from a 100 nautical mile parking orbit, typical once around the Earth, heading on our way out, losing the second stage of the SLS, firing up the Centaur upper stage, losing that, and then firing up the Star 48 EV upper stage, and then finally injecting the spacecraft on its way to Jupiter with a period of cruise of about a year. A Jupiter gravity assist picking up a speed of about another 3 AU per year, and then finally onward and outward out of the system. A lot of discussion, of course, has gone on about, well, which way do you want to go? We're going to be talking about that during the workshop. And again, what we're doing right now is putting together the menu. There's going to have to be further discussion and would have to be a further science definition team in the future to make a decision about what one would actually do. And so that's kind of where we are on our way to the stars, not to get there, but to take that first step. But with this caveat, one of my favorite quotes back from Thomas Edison, that vision without execution is hallucination. And again, this is the reason for pragmatic with a capital P, where we need to look at requirements that have to be commensurate with realistic estimates and funds. And this is going to be what is going to be required if we're going to make this thing real. We have to have a compelling science case for what we do, but at the same time, we have to have a realistic budget from which it could be funded, and then leave this to the other stakeholders in the system to make those decisions. And that's my talk.
Thank you, Ralph.
I don't know where we are on timing, Michael, so over to you.
We are in good time, and invite people to put questions into the Q&A. Some of them we may defer to later if they dive into areas that we know. We have our specialists, our speakers coming up. Others we may want to tackle right now. But I invite you all to enter questions into the Q&A session, into the Q&A tool, to if you want to learn more from Ralph or the others on the panel right now about what Ralph just shared. So Ralph, we've got a question from Stuart. Stuart Bale, last year at the workshop, there was some talk of using 2 SLS rockets. Is that still on the table?
Not in the really in the mainstream. I mean, it did come up. We did take an initial look at it. Of course, you've got a couple of issues that you have to worry about. One, you have to buy 2 of them, which gets back to some of the funding issues. The other question is, how do you put the architecture together? So all of a sudden now I've got to worry about launching 2 of these in fairly rapid succession. So I actually need to have 2 launch pads that are geared up for those going together, and then being able to put them together and use the staging properties from low Earth orbit. And it actually turns out that if you launched 2 of these things to then assemble in low Earth orbit and then boost them further, it's not really quite as good as going ahead and using the power of 1 and then keep building on it as you're still moving out, because you'd have to go into a slower parking orbit to put these together. It's a similar question that was faced by people looking at the Earth orbit rendezvous idea for Apollo, and again, really worrying about the logistics of rendezvousing the upper stages of 2 Saturn V's looked to be like it was getting way too complicated. And as far as I'm watching these. So yeah. Certainly we can use these for studying CMEs. I mean, the idea would be we're not going to just simply go to the end of the mission at the end of 50 years and then turn the instruments on. We would be immediately, I mean, this would be like any other heliophysics mission going out into the solar system. You would want to have the instruments turned on and ready to roll and checked out as soon as possible after the launch. And we would be recording the data and sending it back as we went.
Thanks. And Ron, I believe Ralph's slides are already available at interstellarprobe.jhuapl.edu. Under the agenda, for each of the speakers that have slides, you should find a link to a PDF for their material.
Right. Take a look at the website. What we're trying to do is to make sure that everything that comes out of this is as public as possible. And so we're actually backfilling some of the website from some of the presentations that have been made in the past. It's been a little crazy here, of course, in the last 6 months as we were trying to accelerate getting the website up. But we're working on it. We're getting there, and so keep an eye on it. And you have any questions about looking for any information, please feel free to contact us.
And Andrea Harmon posted in the chat, and I believe this went to all attendees, should be able to see this, the link to the meeting, the agenda, and the rest of the resources that we have available on the website at this point. All right. So it is 11 o'clock, and we have Pontus scheduled to be, I'm sorry, Jim Kinnison's engineering overview scheduled to begin. The schedule says at 11:45. I'm wondering if that was a typo and was meant to be 10:45, or if we wanted to give Ralph a full hour and 15 minutes to go, because we
had planned initially for Ralph to go all the way till I think 11:30 and then take a 15-minute break.
All the way to 11:30 and then take a 15-minute break. Thank you, Jim.
I can start, and we can take a little break, and I can start early if you like. But
I'd like to make sure that that folks that might want to tune into yours don't get derailed by tuning in at 11:45 and not being able to to hear it because we started early. I just wanted to.
So, Michael, you and the other panelists should be asking me some questions until we get some from somebody else in the audience.
Sure. I'll ask you a question, Ralph, and it's actually related to the question that Sadaf Ansari asked about whether or not interstellar probe can help us study solar ejections, CMEs, on its way past 1 astronomical unit. Does a mission like this allow us a unique view of the solar wind and the solar the CMEs and the entire environment of the heliosphere, because it's going to have this continuous record along its trajectory over the course of multiple solar cycles?
Well, it's certainly not going to hurt. I mean, every time that we fly a new mission, we're able to update the instrumentation technology, and so we're able to see new things. Let me give you a good example of that. So it turns out that with the SWAP and Pepsi instruments on board New Horizons right now, we're actually able to measure the properties of the so-called pickup ion distributions in the solar wind. These are they, for the most part, protons, but there's also helium plus, for example, that were originally neutral material. They've been ionized by charge exchange in the outer part of the heliosphere, and then we can see them as part of the distribution function of the protons. Now, this distribution of material has been expected because of the interaction between the solar wind and the interstellar medium. And we can see some slowing down of the solar wind on the Voyagers, but the Voyager instrumentation could never actually see this distribution because we just simply did not have the sensitivity when the Voyager instruments were being built in the 1974-75 time frame. And so here along comes New Horizons. It's the quote-unquote same part of space, albeit in a different part of a different solar cycle. And we're able to make new measurements, and we've been actually able to fill in some of the question marks as a result of having that newer instrumentation. And we're going to have the same kind of opportunity for this. The other thing that's perhaps even more important is that, of course, the Voyagers have gotten out into the nearby interstellar medium. Nothing else has yet. It's not clear whether the New Horizons is going more slowly, whether New Horizons will still have a good power margin by the time that it gets out to that distance well, we'll find out. I certainly wouldn't advocate trying to turn it off, but we're actually going more slowly with New Horizons than with either of the Voyagers by a little bit. And so one of the things we've learned from the Voyagers is that a great deal of the galactic cosmic ray population that gets into the inner part of the solar system and is responsible for some of the background radiation, a great deal of that is actually shielded out by the solar magnetic field that's out at the heliopause. So that and exactly how we're influencing that part of space. I mean, the CMEs are certainly part of that, and we're trying to put all those pieces together. So in terms of being able to have a unique vantage point for the CMEs, yeah, we're going to be able to actually track these disturbances with brand new instrumentation. And I think we'll end up learning a lot, because you learn by being able to look in places that you simply weren't able to look before.
So we have a couple of new questions. Casey Liss asked, what is a realistic timeline and launch direction for Interstellar Probe, assuming a 1.5-year COVID-induced delay? And I'll say that at this point, I don't think that COVID is really delaying this project at this stage. Jim Kinnison, for example, has done a fantastic job of keeping the engineering study on track, despite the fact that the engineers have not been in the same room with each other for months. The questions that need to get answered, they've studied as they can and continue to make the progress that we were supposed to make. And one of our tasks on the NASA contract is exactly what we're doing right now. And the webinar series that we established in the spring, and we've had about a dozen of them so far, to help build the community and share what's going on and share what the questions are that are being asked by the team over the last several months. That hasn't slowed down, despite the fact that so many conferences were canceled and so many activities were curtailed. So if we were a year away from launch, Casey, then maybe we would have a delay because of COVID. But right now, I don't know that it's really going to impact us.
And I can say to Casey, of course, is at APL and has been one of the key members of looking at some of the things you can do with astrophysics and dust from this platform, that if we were to get behind and we were to actually end up getting a budget and a chance to build this, that I'm sure Casey could work 24/7 and we'd be able to pick up in the slack that we needed to.
Very good. We just signed Casey up for a double shift. That's what you get for asking questions, Casey. Wayne Schley asks, baseline designs are looking at 2 RTGs. That's the baseline design for the spacecraft that Jim and the engineering team have begun to put together. How many RTGs is Interstellar Probe realistically able to procure, given cost, schedule, and availability of material? And would more RTGs help? And that's perhaps a question for Jim and Ralph to take on together. But I will say this for all of our participants, that when we hear from June at the end of the week, we'll get a really good current state of affairs from the RPS office itself. But Jim, Ralph?
Well, just to be clear, so June Zakrajik actually runs the RPS office for NASA out at Glenn Research Center in Cleveland, Ohio. And I've actually been working with June now since about 2014, when we were running the nuclear power assessment study. And so we've we have been engaged in the same way that we've engaged Marshall Space Flight Center about the launch vehicle for several years now, before that there was any official money. We've actually been engaging the people at Glenn Research Center, people at the Material and Fuels Complex at Idaho National Labs. This is where final assembly of these power supplies are done. And with the current procurement strategy that's been worked out between DOE and NASA, it doesn't look like that we will have any problem if we need to have 2 of these things. I think if you needed more than that, you would probably be running into some issues with the procurement, but you've also got to get the design to close. And Jim, over to you on getting the design to close on this
Sounds
thing.
good. So the biggest issue with RTGs, I mean, obviously, if we were to have more RTGs, we would have more power available to us, and that would be a good thing. We would also be able to plan a little bit better for some robustness. So for instance, if we had 3 RTGs, we might plan a mission that is, at end of mission, is able to operate on 2. So that would give us some robustness against an RTG failure, for instance, although that's less of a concern, I think, from a reliability standpoint than other parts of the spacecraft. The biggest issue with flying more RTGs is mass. An RTG weighs some 60 kilograms. And in addition to that, you got to put structure on to be able to hold it in place to withstand the launch vibration and the deceleration associated with stage burnout and things like that. And so it's going to slow us down, right? And one of the things you'll see in my presentation is it's about 0.17 AU per 50 kilograms of mass. So if we added a single RTG, you're probably talking about 1/4 of an AU per year slowdown or something like that. Given that we're somewhere in the ballpark of 7.5 to 7.25 AU per year speed right now, given the design we have, that may drop you slightly below the 7 AU per year. Is that a big issue for the science? Maybe not. It would have to be studied, but I think that if we can fit into 2, I would much rather do that so we can maintain the ability to do better than factor 2 over Voyager.
And it would indeed not cost as much to have only 2 rather than 3.
Well, that is certainly true as well, yes. By a significant amount.
All right. So Jonathan Slavin asks, has there been any discussion yet regarding whether or not to choose an ecliptic latitude to take interstellar probe out of the heliospheric current sheet? And Ralph or Pontus or Elena, Elena Provornikova, our lead heliophysics on the science team, if you want to take this question and remind us as you give the answer of what ecliptic latitude means and what the heliospheric current sheet is. I know these things. I hear these things a lot. I don't always remember what they are. And I know that, especially with so many students on board, I want to make sure that some of the more industry terms are well defined for everybody that's joined us today.
Lena, are you there?
She might be on a parallel meeting.
Ah.
But I can certainly take that one. I'm speaking slowly to give her an opportunity to respond. No, that's absolutely right. So the current sheet is sort of the dragged out sheet or magnetic field from the solar wind. It forms this sort of ballerina disc that goes out into the heliosphere. Yes, we have looked at this. So in the previous workshop, we came up with, I think, I'll show it in my presentation, we came up with 6 or so different directions. We documented the high-level trades, the pros and cons for science for all of those. And most of them were actually in the ecliptic plane. You'll see from my presentation that one of the things that bubble up to the top very quickly was, of course, actually to stay near the ecliptic plane, just for energy reasons, to make sure that we have a high speed going out, but also because it is one of the more interesting directions as well. So one of those directions that bubble up on the top was to go about 45 degrees off the nose direction. You'll also see in my presentation, there's an optimization to that in terms of speed, at least, where you go about 12 degrees south of the ecliptic. Then the other ones were to go completely off the ecliptic, sort of 45 degrees or so off the ecliptic. You do get a penalty in speed. There were several scientific reasons for that. One of them was proposed to go out to the sort of jet-like structures that have been proposed from several models. You'll see more of that in my presentation. And yes, we are looking for more ideas out there. And as Ralph alluded to already from the beginning, this is not about deciding a direction. It's about documenting the traits, the pros and cons.
And Wayne Schley will be talking about in some depth about the trajectory trades. And again, to emphasize what Pontus said, you can certainly you can go to the ecliptic North Pole, but it's going to cost you in terms of speed. And so there are trades. So the fastest that you're going to go is if you're very, very close to the plane of the ecliptic.
Yes, and for all the students online, we got to keep those in mind. So basically, what this comes down to is the physics that the Jupiter gravity assist. You're doing a slingshot motion using Jupiter's orbital motion. So you can imagine that if you stay within that ecliptic or the sun's equatorial plane, if you will, you'll maximize the speed. But if you try to go off the orbital plane of Jupiter, you get a high penalty in speed and you slow down. And here's Elena. Good morning, Elena. How's your day?
Good morning, everyone. It's going great. Thank you. So I'm sorry for double meeting a little bit here. So as I understand, we're looking at the question from John, right?
Yes.
So, and I just wanted to add that, so the heliospheric current sheet position changes during the solar cycle, right? So it's in the ecliptic in the ideal solar minimum. So as we go through the solar cycle, the current sheet position will change. The current sheet would, go to larger latitudes. So in fact, given the duration of the mission, we will be able to sample, the different polarities of the magnetic field. So even if we go in the ecliptic plane, we will be able to sample different sides of the heliospheric current sheet as it moves during the solar cycle.
All right, thank you all for that. That was great. So Sanjay says, as a grad student, especially interested in plasma physics and power systems, how can I get involved? Also, are there any alternate fuels being considered for the RTG? Yes, so we had the student session earlier this morning. We have another student session on Friday. And just for those of you who haven't heard what we're trying to do with the students, perhaps Alice can expand on this, but the basic premise here is that just like New Horizons has the student-built dust counter on it, there should be a student instrument on Interstellar Probe. And so we would like the students as a community to begin thinking about what that might be, how it might be crafted, competed, chosen, what is the science that could be gleaned. And so as a student, I encourage you and all the rest of the students to make sure you're on our mailing list, following our announcements via the website, participating this week, and really engage with us as a team to understand what we're doing and how we're moving forward.
And to cut to the chase, Sanjay, because you were on this particular meeting, you are involved by definition, as are all the others out there.
No,
thank you.
Yes, thank you all for being here. He's got a two-part question here, Ralph. Alternative fuels considered for the RTG. I can give the short answer to that, and it's no. The plutonium that is used is the heritage and has the process and the factories and the machines and the approvals to be used, and switching to a different fuel right now would probably add 10 years between now and whatever launch date we end up with. But I imagine you've got a bit more to say about that.
Well, there's an even better solution, and that is it's that out of over 3,000 different isotopes, it really still is the best. And there's a variety of reasons for that. There's actually a write-up if you look on Google and look for the Nuclear Power Assessment Study, NPAS. There's a NASA website where that should come up, and there's a lot of discussion there about using radioisotope power systems. We touched, I believe, when we wrote that a little bit on this topic. Right now, the European Space Agency is looking into using americium-241, which is inherently heavier. It's got some other issues, but they've got access to it. Plutonium-238 is the best solution if you're going to build an RPS, again, for a whole host of technical reasons. And anybody that's really interested, I'd suggest to take a look at the NPAS report.
Now, Andrea just dropped that link into the chat for everybody to see if you'd like to use it. Thank you for the questions, Sanjay. Alan Stern asks, has there been any discussion with internationals of joining us to fund a 2-spacecraft mission launched in different directions? So we have had multiple discussions with international scientists about helping to craft the basic parameters for the mission and what sort of collaborations at the science level might happen. We have begun some discussions with different folks in Europe about about different elements of a single mission, but we haven't really opened the ball in terms of a 2 spacecraft mission that would go in different directions.
Well, there's a footnote to that.
Yes, there is.
We've actually, so actually one of the things that we have been doing is reaching out to the international community. There's actually a now virtual session at COSPAR in session PIR.1 that has a great deal of international participation. That's going to be at the end of January. If you can get to Sydney, Australia, well, they're going to have a piece of it that's live as well. I will not be attending that. So it turns out I was also in, several of us were at a workshop run by the Russian Academy of Sciences in the summer of 2019, talking with them. Right now they were saying, well, you know, this is an expensive undertaking, and they were looking at perhaps having, you know, being able to provide another spacecraft, as had been discussed, for example, in the past with on some early iterations of Solar Probe. But nonetheless, we're keeping those communications open. And also, right at a year ago, the International Space Studies Institute, I think I got that right, ISI, which is out of Bern, Switzerland. They have an office also in Beijing, and so I was in Beijing right at a year ago, talking at that international gathering about our plans for this. The Chinese have also been talking about an interstellar probe mission consisting of 2 spacecraft, and without as high of a flyout speed, but looking at going in 2 different directions and diametrically opposed to each other. And of course, anybody else that wants to fly out there, we're certainly, you know, this is certainly something that is important for international cooperation. And quite frankly, you know, I've told people that, you know, in other countries that, well, a way that, again, international contributions and being part of this as an international effort to be helped is to help with getting the data back, and by being able to provide additional telecom communications here on the ground for the ground segment. So there's nothing right yet about all of this. I think people are interested in finding out where we're going to come out with respect to a budgetary estimate. I know that a lot of the European budget right now is pretty full for quite a few years going into the future with their current plans, and haven't heard anything since for about the last 4 months from our Chinese colleagues. So I don't know what their current status is about that, but I'm sure we'll get an update. We're supposed to get an update at the COSPAR meeting at the end of January. So certainly the discussions are continuing.
One note on the on what we did learn from the Chinese researchers was that their 2 spacecraft scheme would include 2 relatively small and not very highly capable craft. The scope of what they were talking about was not as ambitious as what we are discussing. In addition, they were going to be going not just slower than the designs that you'll see this week from the Interstellar Probe team, they were going to be going significantly slower than even New Horizons is going. They do not have the launch capability to really throw a mass out at the speeds we're talking about. So they're calling it Interstellar Probe. I think they were talking about 50 years to get to 100 AU. So it was fascinating to see them putting this together. It was one of the notional missions that they wanted to put into their possible planning. And we'll see in January where they stand now. One thought that I've had, Alan, and everybody, and I welcome more discussion on this, is related to another question we got earlier about a 2 SLS launch. Just like Voyager had 2 launches within a short period of time, is there a mission architecture here where 2 launches happen and 2 spacecraft go in different directions within a short period of time? And given such a long mission, it doesn't have to be right on top of one another. Is there an efficiency there? Is there a giant leap in science return there? I don't know the answers to these questions, but they're very interesting. to try to figure out. Okay, let's see. So we're at 11:20. Jim's going to begin at 11:45. We could take questions for a few more minutes if anybody has more they'd like to discuss right now. If not, and we can wait a minute or two, I recommend that we let everybody take a break, because this is going to be another couple hours today and then more hours tomorrow and later on in the week. And rather than Zoom everybody too hard, I think a little bit of a break is a good thing to do. So we'll wait another minute or so to see if there's anything pressing anybody wants to ask. But I recommend that all of you do whatever you like to do when you get away from your computer for a few minutes. Go outside, take a breath, stretch, get some food, get some water, and then get back to us at 11:45. And that's when Jim's going to start talking about where the engineering team has gotten to and what comes next in terms of the products that they're creating and the work that we have, not just for the rest of this year, but through next year. And with that, I'm going to mute my computer and stop my video, and I'll be back here a little bit before 11:45 and kick things into work again. Thanks, everybody. Hope you have a good break.